The average rate of change is the slope between 2 points. You have point P, which is x1, y1, and point Q, which is x2, y2, or x1, f of x1, x2, f of x2. So the average rate of change is just that. It's the change between these two, actually between these two values over this time period. Which is, again, it's, and we also define H as the difference between x2 and x1. So that's the average rate of change. The instantaneous rate of change is the rate of change at 1 point on a curve. Why is on the curve so important? Because if it was a straight line, the slope's the same everywhere. So once you see the equation, linear equations, you know where the slope is. Curves, though, curves are created by polynomials, which have higher order, higher degrees, which again, it's at some points that can go up, some points down, and they can do that many, many times. So that's what we're gonna have to look at, would is instantaneous rate of change. For the instantaneous rate of change, we have to relate to 1 point. And how far it is, how far is the second point from that first point? So that's what we're looking at here. And as h goes to 0, then we get to the point, that single point. So that is, in a nutshell, what we talked about the other day. All right. So now we're going to relate this to limits. So as h approaches 0, the instantaneous rate of change approaches a single value, the slope, actual slope at that point. So that's what we're saying here. The way we show that is we're taking the limit as our x values approach a specific point C of the function, and it approaches what's called the limit point. So when you actually get to that value, f of c is equal to that limit value. So that's what we have to get to in section 3. actually, what was 3 actually called? That's the definition of the limit. All right. So the way we define the limit is this. Let f of x be any function on an open interval about or containing the value c. As we learned last time, it doesn't have to exist at c. It just has to exist within that that open interval. All right. The limit of our function as x approaches c is L. As x approaches c of f of x, that approaches some value L. Okay, now comes the important part, because all we've done is saying that given any curve at some value point c, because this is our x values, this is our y values, we know that the function exists on any point along the line, and it has to be an open interval. So all those points have to exist because it has to be a function. Now, what happens at c, that's the point in question. That's why whenever we do this in an equation, the c value we pick are only the ones that make a difference. In other words, if we have a fraction, what is the x value that makes the bottom 0? Or so the c values are chosen specifically for a reason. So now, to further prove this, that this is true, for every value epsilon, it's got to be positive, because we only deal with positive values here. It's hard to describe negative distances, because epsilon is a distance. There exists a that's Dallas County again. There exists a value delta greater than 0. It's positive also. That shows this, that the difference between our function and the limit value is less than epsilon when the it has to be positive also. So our y values, the function itself and the limit. Here's the limit. It is less than some value epsilon. Epsilon and delta are distances. They're very small. So what they're saying here is, let's pretend this is 1 and this is 2, and this is our value here. We can get infinitely close from both sides. In other words, making our epsilon, now actually this is our delta. Our delta is the x values. It corresponds to certain y values. This distance here is our epsilon. So the distance in the horizontal is our delta. The distance in the vertical is our epsilon. So as epsilon becomes very, very small, that means this boundary gets closer, closer, closer to our limit value. It corresponds to our x values as delta gets smaller and smaller and smaller. So the smaller delta gets, the closer it gets to some value c. That means the corresponding y values gets closer to our limit value L. That means epsilon gets smaller and smaller and smaller and smaller, smaller, smaller. Right, so that's what the formal definition looks like of a limit. It has to exist on this plane right here. So you take the function itself minus the limit. Is that some whatever epsilon? We don't define that just yet. We'll do that during the process. And it has to correspond to these values of x. It has to be greater than 0. And it's going to be because it's absolute values. But x minus, so whatever value x we pick, the closer we get to c, the limit point c, it gets smaller and smaller and smaller. So that's the formal definition of a limit. It's called the epsilon delta proof. Let's look at an example. Okay. Let's say f of x. The one I'm using is from. So that equals 5x minus 3. We'll start with that. We're going to use epsilon delta proof for this one. All right, so first thing you do, plug C. Remember, this is x goes to c of f of x equals L. We first plug C into f of x to find L. So that's the first thing we got to do. So 5 times 1 minus 3. 5 minus 3 is 2. So this is our value L. Now, it's important. Notice how I put parentheses around these two. If we didn't, then it's only limit of the 5x, not the 3. So you have to make sure that these things are very important because this defines our function. All right, so let's define what we have so far. F of x equals 5x minus 3. The limit equals 2. And the c value is equal to 1. And again, we don't know what epsilon or delta are yet. All we know is that they have to be greater than 0. All right, so let's look at this. All right, step 3. Find delta, then find epsilon. We find delta by using the x values. And we define c as 1. Then we defined, that's the first equation we'll need. Then we define epsilon. Remember, epsilon was f of x minus L. Well, L, we figured out was 2. So let's go from there. Start with epsilon. Why do we start off with epsilon? Because we know most of the things about it. We know f of x is 5x minus 3. So we can simplify this. 5x minus 3 minus 2 inside absolute values. All right, so now they both have a 5 in common, so we can factor out a 5. We need to have this equation. We don't finish this until we get to that, because, well, we divide both sides by 5. So x minus 1 is less than epsilon over 5. Because now we have a connection, because x minus 1 is what this is, and that's less than delta. So since we have 0 is less than x minus 1 is less than delta, we know that delta equals epsilon over 5. All right, so far so good. Which we, now if we look back here, we could define the actual value of epsilon. Once we know what delta is, we find the absolute value of delta. So this is the important part here. Now we have how close each of these are going to be. Remember, epsilon deals with the y values, and delta deals with the x values. So the smaller the closer we get to C, we get even closer to the limit value. This one goes to C, this one goes to L. Remember, this is the vertical ones. So the smaller this becomes, if we divide it by 5, we get even closer. All right, so that is what we're trying to prove here. All right. Let's look at another example. Saying f of x equals no, let's make it 5x. No, we just did that. Let's just do 3x straight up. So we have 3x. Let's say, since this is a linear equation, doesn't matter what value we pick. we'll pick 2. The first thing we gotta do is find L. So 3 times 2 equals 6. So L equals 6. Remember, this is our C value. This is our L value. Start off finding delta. We have to define our X. Remember, X is the independent variable, so we have to find the independent variables first. So we have 0, X minus 2 is delta. And from there, we have find f of x minus L is less than epsilon. The limit we said was 6. So what is f of x? F of x was defined as 3x. We can factor out of 3 here. Divide both sides by the coefficient. Okay, so we have the relationship now. So we have x minus absolute value of x minus 2, which is what we're looking for. Because we know that absolute value of x minus 2 is less than delta. So then delta equals epsilon over 3. So again, this proves, because these values are getting smaller, this proves that that gets a lot closer, infinitely close to our limit value, and that's what we're looking for. I have to plug in my headphones again. So let's try this next one. F of x equals 4. So if we plug that in there, if we plug it in our function, so we have the limit as x approaches 2 of 4, the answer is 4. So this is our C, this is our f of x, this is our L. So we find our value, this equation first. So we have f of x, the limit is 4. This is true when this is true, x minus c. And the c value So what can we do from here? We don't, because it's a constant term, because our f of x value is 4 minus 4 is epsilon, that equals 0. Okay, now there's a problem here, because 0 is not strictly less than 0. It's equal to. So what we have to do is we have to find another function that's within our domain, within that's not equal to 2. So let's just use x. So we're using f of x as just being x. So f of x minus 4 when this is true. Epsilon, I'm sorry, not 0. So these functions are different. What does that mean? We can't find a relationship between epsilon and delta. The reason we can't is because it's a linear equation. It's a horizontal line. Because this made 0, 4 is our limit. It's always going to be 4. It's a constant term. So get quadratic equations now. Fx equals x squared. It has to be an operable. Let's say x is 2. Oh, it's x squared. At 2, it becomes 4. So our limit value is 4. Just plug in our values and work them out. So when you algebraically, when you drop the absolute values, what happens to the solution? It can be positive or negative. Add 4 to both sides. Negative epsilon plus 4 is less than x squared is less than epsilon plus 4. Get rid of this with the square root each term. So the square root of negative epsilon plus 4 is less than x is less than the square root of epsilon plus 4. So there is our range that we look at it. So what we really have is our value of x is within the bounds of 2. That's what it says, because it's contained within there. So our values of x here, which means that if we look at our graph, -2 and 2, our c value could be anywhere within there, which means our limit value can be anywhere within this range. And that's all it's telling us. All they're really telling us is, does the limit exist? Well, yes, it does, because here's my domain and here's my range. Yeah, so what it's saying here is our solution is somewhere within there. Let me find an example from the end of the section. Our question. Okay. F of x equals sorry. Oh, I didn't do it one. What if I gave you an epsilon? Because in the other examples I gave you I just gave you the values themselves. But what if I defined an actual value for epsilon? So would it get the same way? F of x is now going to be now we know we have to be within that amount. So we look at our limit as because we need to find what our limit's going to be. So if we plug in our value, (0.01 plus 1 is 1.01. So x plus 1 minus 1.01 is less than epsilon, which is less than 0.01. That's gonna be. Let's just pick one. Let's just pick one, because that's gonna make it a little bit too hectic. We're saying our limit is 1. So we have x plus 1 minus 1 is less than 0.01. 1 minus 1 cancels, so x, absolute value of x is 0.01. Drop the absolute value sign. So what that's proving is our x values, our domain has to be between these two values. Now we have to connect them back to the original function. How do we do that? So I did define the value c. Okay, let's see. So it has to be 0. Must be 0. The reason it has to be 0 because remember I changed the answer. I had x plus 1, and what value x would make it equal to 1 if x is 0? So that's my limit. That's the x value. So I have 0, absolute value of x. So now if I look at this and I look at this, this says my delta function is equal to 0.01. Because it's so small, that's why the epsilon and the delta values are the same. So that's the formal definition, formal proof of the epsilon delta of finding a limit. Okay, so let's recap. The first thing you have to do is find steps. Given f of x, given some function f of x, and some value c, find L. Plug it in there. That gives you L. Define epsilon. Work it out. Define delta. Work it out. So the x minus whatever number you have in there should be the same in both equations. Then usually what you'll end up with is because the delta is just x minus the limit point, it's always going to be just an integer. So you'll usually end up with this. or any number, the number could be any integer. And there you have it. That's what you're finding. So what do y'all think? Anybody?
So you said basically what you find for what were you calling it? Like the E.
I'm sorry. I never wrote those down, did I?
It's okay.
They both mean distance.
All right. So if you basically find the epsilon, that is going to be your delta, right?
Well, once you find epsilon and delta, once you find these two values there, because remember this one here, the epsilon could be a fraction. Remember the first example we had? We had
Yeah.
5x minus 5 is less than epsilon.
Mhm.
So I factored out what I could. And then I divided by 5. So I have to have the absolute value by itself. But the other one, the delta one, that's always going to be just a delta, because this will never, it starts off with an x, so you can't factor anything out. The epsilon starts off with f of x, which itself could be a polynomial of any size.
Okay.
So yeah, so in this one, the epsilon one, you may have a coefficient to factor out, and if you do, you can't have a coefficient here, so you'll have epsilon over some number.
Gotcha.
And if nothing factors out, then it's just epsilon. It's just delta equals epsilon.
Gotcha. Okay.
Yeah, but this is what shows us that the closer we get to our value c, the smaller delta gets. Because epsilon is divided by 5, the distance here gets even smaller.
Okay.
So if this was 2, or so if this was 10, so between here and here was 10, between here and here is 2 because I divided by 5. So as that one gets closer, this one gets even much closer.
Gotcha. Okay, thank you.
And we will be faced with some situations where limits do not exist. Jump functions, discontinuous functions like this, or rational functions like 1 over x, or what you call oscillation functions. And sometimes, for example, oscillation function is like the sine and cosine. If we took the limit of x going to 0 of sine, what would that give us? What's the sine of 0? 0. The reason being, because if we look at our graph, the closer we get to 0, the graph is approaching 0 from both sides. So when this one, as we get closer on the X, the Y values get closer. So it's both sides are approaching this solution. That's why it's a limit. It doesn't have to exist like our last example yesterday or Monday showed. If we had a jump discontinuity, let's say this is 4. So the limit as X approaches 2 of this function as a whole is still going to be 4. The reason it's going to be 4 because as we get closer to our C value, our Y values get closer to our limit. So as we get closer to this one, they get closer here. So it doesn't have to exist. It just has to appear to exist, approaching it. We have to get infinitely close to it. Let's say I had sine. If X approaches pi, what is cosine of pi?
-1.
-1, yes. Remember, this is our limit function. This is our limit value. It never said anywhere that the limit has to be positive. Our only conditions that we had were our epsilon delta both have to be positive. They have to be a positive distance. And then from there, everything else is defined. So, yeah, so nothing's ever said about f. The function could be anything, but the limit itself, it could be positive or negative or 0. Let's see. Let's do one more. I saw one that had to do with radicals. We'll say 6. And epsilon equals 1. What you're asked to do is find a delta that is greater than 0. As X approaches 5 of X minus 1. So what's remember, the first thing you have to do is find the limit with no Ellis. So plug in this value in there. Our limit value is 2. This is our C value, this is our f of X, and this is our L. Epsilon. Why do I put delta there? So I have absolute value of X minus 1 minus 2. The epsilon value we have was defined as 1. Okay. Algebraically, we can't do anything inside here. So we have to get rid of the absolute values. If you could solve it algebraically and simplify it, perfect. If not, get rid of it and work it algebraically. So first thing, we add 2 to everybody. Two minus 1 is 1. 2's cancel there. 2 plus 1 is 3. Remember, we're trying to get to x. To get rid of the radical, we have to square it. So we square both sides. Those cancel. 3 squared is 9. Get the x by itself. Add 1. All right. So we have our x values there. Let's see. 0 less than x minus c. Right, so we have to now prove that. Again, we drop the absolute value signs. Because we can't do, we have to try to make it equal that. So we have to get x by itself. Add 5 to both sides. So negative delta plus 5. And delta plus 5. So we have x's equal the same. So we look at both of those. So we know that so subtract 5 from both sides, you get negative 3. Change the signs. We have one solution. And we have a second solution. Because remember, what we have to now look at this tells us that our domain has to be between 2 and 10. So look what we have. So, which one's more viable? We want the smaller ones. Remember, we had x minus 1. So these are our values we're looking at. X delta equals 3 will give us a closer representation of what's going on. So what we know is for our function, which is x minus 1, the limit, and that was 1. When c was 5, and we use 3. Because if it was 5, x minus 5 equals 5. And that's not within our bounds of 210. So that's why we have to use 3. We want it closest we can to the x value, or to the c value. So this is our answer. That this proves to us that the limit exists and it's viable. All right. Oh, did y'all get the message of all the solution sets I sent out?
The ones from last week?
I sent them
Or
earlier
this week,
today.
sorry?
Yeah, I thought I sent them earlier.
Oh, yes, I got it.
Okay, good,
I
good.
get it.
Yeah, I couldn't find all my lecture notes in the PDFs. I must be on my other computer, but those were on my YouTube channel, so I just sent them out to y'all. And we'll fill in the blanks as we go along. Right, any questions? No questions? All right, everybody. Then do your best you can, and then if you get stuck, give me a holler. On Monday, we'll answer whatever questions you have over the homeworks, and then we'll move on to the next sections, because now we're getting closer. Now we're getting closer to actually using what we've learned to start defining calculus. We've built up the pieces. We looked at, remember when we first started talking about the slope, the review of algebra, to learn how to do the slope, the difference quotient. The difference quotient was used to define average rate of change. And then also we looked at the distance quotient to find the instantaneous rate of change. Those all were used to get us where we are. And here is that now, once we have our values, how accurate are they? Are they within a certain boundary of possibilities? Now, once we have proof of that, we have to look at, okay, the functions have to be continuous, the limits have to exist, but what exactly does it mean that a limit exists? What we're going to look at next is for a limit to exist, the values have to approach C from the left, and the values have to approach C from the right. So now we're going to look at one-sided limits, because both sides have to exist for that to be a true value. But that's coming up next week. All right, so go make snow angels and watch TV.
Thank you so much.
Thank you.
So how did this work out? Was it as scary as you thought?
No, I actually enjoyed it.
Yeah, I see. As I'm saying is, if we have to do it online, this is exactly. I mean, this is much better in the classroom. Because first off, I can't get that computer to work in the classroom. Here, it's much better. Because if you don't want to, you can always ask me to block out my face, and then you won't be scared.
Yes,
All right,
no, I
everybody.
really liked it. Thank you so much.
You are very, very welcome. Y'all have a great, safe weekend.
You too. Thank you.
You too.
Bye-bye.
Bye.